back. Now we're going to do electric field, electric force problem. We're going to calculate what the electric field of a ring charge is on the central axial line a certain distance away from the ring. So first we could do it for general charge Q and a certain general radius R and a certain distance x. And then after that, if we want, we can then put in some numbers and find out what this is. So let's say I want to figure out what the electric field here is. So what approach do I take? Well, we're going to use symmetry here. We're going to take a piece of charge here called dq, and we're going to say the electric field of that charge is radially emanating away from the charge, dE. We'll call that dE1. Then we'll take a piece of the ring on the bottom, dq, and then the electric field of that will be radially emanating away from that, dE2, right? So by symmetry, we're going to say that the y component of these vectors cancels and only the x component survives. So if I put this to the tip of this, I get a vector dE total, right? So dE total is equal to 2dEx, right? Only the x component of the electric fields survive. So if I define this angle as phi, and that's going to be the same angle as phi here, and then this is the distance x, and then this is also phi, and this is phi, okay? So therefore, only cosine of phi will survive. dE total is equal to 2dE cosine of phi. And dE is equal to what? Well, it's the electric field of a point charge, k dq over r squared. dE total is equal to 2k dq over r squared cosine of phi, where r is the distance from that point to the point of interest. Okay? So then we integrate this over half of the ring. We don't have to integrate it over the full ring because we already took into account the symmetry that the ring has from one part to the other part. So we already are doubling it. So when we integrate it, we only integrate half the ring, right? Now, one of the interesting things that you'll see here is that this ends up not being an integral problem. Why? Because no matter where I am on the ring, the angle phi is the same, and the distance r is the same. None of them changes. So basically, think of this as a ring like this. The ring is coming out of the board, here, out of the board, and it's going, wrapping around, and then here it's going into the board. If I'm on the central axial line, no matter where I am from the, no matter where I am on the ring, I'm equidistant from that point. And the angle phi is the same. So this is phi, and then this is coming out of the board. So it kind of, if you are right here on the ring, it would look kind of three-dimensionally, it would look like this, right? And then this would be radius r, and then this would be the distance x, this would be phi. And then this is r. So the angle phi stays the same, r stays the same. So no matter where you are on the ring, you're always equidistant and the angle doesn't change. So all of these things come out of the integral, okay? So E total is going, the 2 comes out of the integral, the k comes out of the integral, cosine of phi comes out of the integral, and then r squared comes out of the integral. You have integral dq, right? When you integrate integral dq, what do you get? Q, okay? But remember, we said we have to integrate only half of the ring, right? So if we integrate only half of the ring, when I integrate dq, I get q over 2. Q over 2, which is half the charge of the whole ring, right? That 2 and that 2 will cancel, 2 and 2, and then my final answer will be what? E total is equal to k over kq over r squared. Well, r is equal to x squared plus r squared. x squared plus r squared. And then cosine of phi is the adjacent x over the hypotenuse r, which is basically x squared plus r squared to the 1/2 power. So this one was r squared, and then this one was a single r. Then you just multiply them, you get to the 3/2 power. So my final answer is E total is kqx over x squared plus r squared to the 3/2. And if there's another charge there, little q, what would be the force on that charge? Well, once we found the electric field, then the force on the charge is just simply the electric field times the charge little q. So F is equal to QE, which is equal to KQQX over x squared plus r squared to the 3/2 power. Okay? So one of the things we can do when we derive this kind of equations, this is the equation for the electric field, and that's the equation for the force, we can see if it makes sense. Take the limit of this as x goes to 0, take the limit of it as x goes to infinity, over, and then if you put x is 0 here, it's going to be negligible compared to r squared. So you're basically going to have r squared to the 3/2, which is r cubed. So the behavior of the electric field when you are near the center, its behavior is the same as that of a linear function of x. When x is exactly equal to 0, the electric field is 0, right? So when E of 0 is 0. Okay? If you are near the center, but not necessarily at the center, the electric field will increase as a linear function of x. So what happens if you have a positive charge here and you have a negative charge placed near the center, negative q? What do you think is going to happen? Well, the negative q is going to experience a force towards the center, and it's going to drive it towards the center and then back and back and back. So if you look at it from the side here, so let's say you have the ring here, and then you have here negative q, the electric field will exert a force on it this way. But since over here the electric field is to the left, by the time the charge comes to the other direction, the force on it will be back, right? So it will make basically simple harmonic motion around the center, right? So we could actually ask, what is the frequency of this motion? How fast will they go? Well, what is the force on the charge? On the charge q? It's going to be kqx over r cubed, right? Remember, back in mechanics, when you have F is equal to negative kx, and that's equal to ma, this is basically the spring problem, right? A mass connected to a spring oscillating back and forth. Notice that you have Hooke's law, K, right? And then this is linearly proportional to the distance of the stretch of the spring. We found that omega is square root of K over m, right? So the radial frequency of oscillation of the mass is square root of the spring constant over the mass, and then the frequency of oscillation is 1 over 2 pi square root of K over m. So anytime we have something that looks similar to that, in this case we have the force on the, well, the charge is actually negative q, so I should put here negative. Negative k q, little q over r cubed. So what is the spring constant in this case? It's basically this part, right? K, big Q, little q over r cubed. That's this. And then it's going to make that little object, let's say that object has a mass of little m. So what's going to be the omega of the motion now? Omega is going to equal square root of this whole thing, k, q, q over r cubed, and then the mass of that object. And then if you want the frequency of oscillation, you say 1 over 2 pi. There you have it. So the k is the 9 times 10 to the 9th, the constant of Coulomb's law. the two charges divided by the radius of the ring cubed and the mass of that particle. That's how quick it will oscillate. So a little bit of a limit exercise led us to a pretty interesting conclusion. Now, what's going to be the limit of this function as x goes to infinity? Okay? So let's find the other limit. Limit as x goes to infinity of the electric field, kqx over, now when this is infinity, r is negligible compared to it, and you will have x squared to the 3/2 power. Okay? kqx over x cubed, then you have kq over x squared. Okay? Now, notice that when you go out to infinity, the electric field of a ring, and therefore similarly the electric force on a charge that goes out to positive infinity, resembles that of the electric field of a point charge. So the ring begins looking like a point charge when you are quite far away from the ring. Okay? So it makes sense, and it's a very interesting result, and it actually proves that our equation was right and it made sense. Okay? So next I will do the electric field of a plate charge. Okay? So what I will do is put a solid plate, and then we'll see how to do those kind of problems. Okay? Thank you.